Molecular orbital theory. We've talked about Lewis theory and valence bond theory, and now we're going to talk about molecular orbital theory. In this theory, the orbitals are calculated for the entire molecule, not just each individual atom. We've talked about quantum mechanics and how the electrons can be described by a wave function. And we talked about the Schrodinger equation. So the Schrodinger equation is great, but the problem is that you can't solve it absolutely, even for a very simple molecule. So what they do is they put in a trial function and see how that works, and then they adjust accordingly. And so they use a computer to calculate the energy of the trial function using the Schrodinger equation, then they optimize it to minimize the energy. And of course, we're just trying to describe what nature is doing, and we cannot do better than nature at minimizing the energy of the orbital. But that's where all of this ultimately comes from. So molecular orbital theory takes those atomic orbitals and instead of hybridizing them on individual atoms, combines them and into what's called a molecular orbital. So it's orbitals that are for the whole molecule. So LCAO stands for linear combination of atomic orbitals. So we use a linear combination of the atomic orbitals to make this molecular orbital. It's a weighted linear sum of the valence atomic orbitals of the atoms in the molecule. And this is the simplest trial functions that work reasonably well. So we take the valence atomic orbitals of all the atoms in the molecule, and we mathematically combine them together. Valence bond theory combined the orbitals on an individual atom into the hybridized orbitals. So we had the sp and the sp2, et cetera. So we're not going to have hybridized orbitals here. We've got molecular orbitals. These orbitals are often delocalized, meaning they're spread out over the entire molecule, whereas the hybrid orbitals from valence bond theory are localized on an individual atom. Any questions yet? Let's look at a simple molecule, about the simplest we can get, H2. So one of the molecular orbitals for this molecule is an equally weighted sum of the 1s orbital from one atom and the 1s orbital from the other atom. So we add these together and we get this shape. This is a bonding orbital. It's given the name sigma 1s. Sigma is for the shape. It's cylindrically symmetrical along that bond. And the 1s label here is because it's a combination of 1s orbitals. This is called a bonding orbital, and it's lower in energy than the individual atomic orbitals that it came from. If we're combining two orbitals, though, we need to end up with two orbitals. The other orbital is made by adding a 1s orbital to the negative or opposite phase of the 1s orbital from the other one. So it's like subtracting. So here we took these and we added them, and here we're subtracting. And we end up with this, where now there is a node between the atoms. This is called an antibonding orbital, because it's not just non-bonding, it's actually against bonding. Bonding causes the two atoms to be brought together, and this causes the two atoms to be pushed apart. This antibonding orbital is higher in energies. Here's the energy of the original atomic orbitals. When we combine them in this way, it goes up. This is given the designation sigma star 1s. That star tells us this is an antibonding orbital. What we're doing here with the adding and the subtracting, this is the constructive interference of these two waves, and this is the destructive interference of those two waves. Okay, and so that's why we get this cancellation in the middle.
Why is one destructive and one constructive?
It depends on whether they're in phase or out of phase.
And what do you mean by that? Like,
Well, like with waves,
oh, okay, yeah.
right? So
I
we
got
had,
you now,
yeah, but just for people who might not get it yet. So this would be in phase, and then these add up and get bigger. If they're out of phase, then when we add these together, they cancel each other out. And so that's the idea here. It's actually easier to see when we look at combining the p orbitals.
But that makes a stronger bond than when they're in sync or in phase?
No, this makes a weaker bond.
Okay.
Yeah. So when we're looking at bonding, we want to increase the electron density between the atoms. Here, there's no electron density between the atoms. And so this place of no density is going to push them away. In the bonding orbital, we have increased electron density between. So here we're not talking about just overlapping orbitals, but we're actually combining the wave functions constructively and destructively. One makes a bonding orbital, one makes an anti-bonding orbital. Yes?
What if they're just like a little bit off sync? Is that just considered constructive or?
What if they're a little bit out of sync? I don't think that's possible.
Okay.
So these orbitals have a phase, and in the S it's kind of hard to see because it's either one or the other. So our analogy with waves on a string or waves in the water is limited. Those sorts of waves can be a little bit in phase or a little bit out of phase. These are either going to be completely in phase or completely out of phase. So putting these two together with destructive interference, we get an antibonding molecular orbital. Putting them together with constructive interference, we get a bonding orbital.
And what exactly does destructive and constructive mean?
So when waves are combined, if we take two waves that are in phase and we add them together, they get bigger. And two waves that are out of phase and we add those together, they cancel each other out. It's like a trampoline, yeah. So this bottom one, I should have drawn them in reverse. This is destructive interference, and this is constructive interference. Constructive interference increases, and destructive decreases the wave. So when these interact destructively, then we get this node in the middle. This is going to be higher in energy than this bonding orbital.
And what is
Go ahead.
What is the sigma under there standing for in this diagram?
Sigma stands for the shape, which is symmetrical. It's a cylinder.
Okay.
So if you were to put your eye over here and look this way, you'd see a cylinder, and it's symmetrical. You'd see that for both of them. That's why they're sigma.
So the anti-bonding molecular orbital is still a bond?
It's not a bond. No. And we're not really looking at individual bonds. So here's the big disclaimer. We are looking at the very, very surface of molecular orbital theory with the purpose of giving you enough understanding so that when you get to organic chemistry, you can understand the resonance and the aromaticity of cyclic compounds. We're not going into depth, and so there's some stuff that's just not going to make a whole lot of sense. We're not talking about individual bonds. We are going to be able to look at these molecular orbital diagrams and predict whether that molecule is stable or not.
So I was reading this and I understand it, but like, I'm just kind of, when would this happen?
Well, when would this happen? We think this happens in any molecule. So valence bond theory is one explanation, and it's great for a lot of things. Molecular orbital theory is a more sophisticated, more involved, harder to understand theory, but it explains more situations that valence bond theory doesn't understand. So I would say this is probably our best explanation of bonding currently. So a molecular orbital diagram, that's what this is, shows how the two individual atoms combine their orbitals to make the molecular orbitals. And so when we draw these, we're only looking at valence electrons. We draw the valence electron diagram over here for the one atom and the valence electron diagram over here for the other. And then we combine them. And so we have a 1s and a 1s. They're going to combine constructively to make a bonding orbital. This is the sigma 1s. And they'll combine destructively to make a sigma star 1s. This is higher in energy. So we draw the molecular orbitals, and then we look at how many valence electrons are there. Well, there's two. There's one here, and there's one there. They are going to fill up these molecular orbitals the same way that we've seen them fill up atomic orbitals. So they're going to go into the lowest orbital first.
So for these, is it going to be the same atom a couple of different times? Like for example, so for this example, it's H2. So would it be like OH or like
Yeah, this happens between dissimilar atoms, and we'll look at that towards the end of this section. But we're going to start out with the simple ones. Yeah.
So this is showing the two possibilities, right? That's what's
When these two orbitals combine, they form two new orbitals. This one forms and this one forms. This one is occupied for this particular model. That one is not occupied, but it's there. Just like in valence bond theory, however many orbitals you start with, you have to end up with the same number of orbitals. You can't lose orbitals or gain orbitals. So if I start with two orbitals, one from each atom, I need to end up with two orbitals.
okay. And then because the wavelengths match up, then they're going to sit in the H2 molecule.
Because this is lower in energy, the electrons are going to go in there instead of going into the antibonding. If this one's full and there's more electrons, then they'll have to go into the antibonding orbital. And we'll look at some examples of that. What we call bond order for diatomic molecules, and we're only going to look at diatomic molecules, is the number of electrons in the bonding molecular orbitals minus the number of electrons in the antibonding orbitals, and we'll divide that by 2. So for hydrogen, the bond order is 2 minus 0 over 2. Let's go back to the diagram. We're looking at the number of electrons in the bonding orbitals. There's one bonding orbital here. How many electrons? 2. So it's 2 in the bonding. And how many in the antibonding? 0. And then we're going to divide that by 2. And so we get a bond order of 1. Yes?
So will it give us this kind of diagram, or do we have to make this diagram first in order to do that?
Well, on the exam, you'll probably be given the diagram.
Okay.
In homework, you're going to have to draw it. Yeah.
But it's easy though, you just do the valence electrons on both sides and then combine them, right? Is that what
Yeah.
it is?
Yeah.
Okay.
It's easy. You just combine the valence orbitals.
It's kind of like off base, but does nitrogen make triple bonds? Ever?
Nitrogen does make triple bonds. Molecular orbital theory, we don't really look at double, single, triple bonds. But we're going to look at nitrogen and see what it does. No, just so you on.
Which is diatomic stuff.
I have a question every time. Stop.
Well, yeah, I see stretches and yawns, and I
Well,
just
the
don't
one
know.
for valence electrons, there would be no reactions.
Yeah, valence electrons is really important. Okay, so that's how to calculate a bond order. What does the bond order mean? If the bond order is positive, meaning larger than 0, a chemical bond will form. It will form because in forming, the electrons have lower energy. And generally, things that go to lower energy are going to happen. If the bond order is 0, a bond will not form because there is no energy benefit to doing that. If the bond order is negative, that means it's higher energy for the electrons to form the bond, and they're definitely not going to do that. Okay? The higher the bond order, the stronger the bond. Yes?
Now, is it over 2 because there's 2 of them bonding? So it'll always be over 2?
It'll always be over 2. Let's look at an He2 molecule. You've ever heard of an He2 molecule? Didn't I tell you that helium doesn't form compounds? Well, let's look at what would happen if we put 2 helium atoms together and tried to get them to bond.
I'm sorry, it's number of bonding over number of antibonding.
Number of bonding
Minus
electrons
number of
minus antibonding divided by 2.
Yeah, that's-
So here's the helium atom. Its valence electrons are 2 valence electrons in the 1s orbital. And here's the other helium atom. And these 2 orbitals are going to combine, just like the other one did, linear combination of atomic orbitals. We're going to get a sigma 1s and a sigma star 1s. So the molecular orbitals look the same as they did for the hydrogen molecule. But now we have 4 electrons. We have 2 here and 2 there. And so we need to put 2 in the bonding orbital, and then the other 2 are going to have to go into the antibonding orbital. That changes the bond order. 2 electrons in bonding minus 2 electrons in antibonding. The numerator is 0, and you divide by 2, and it's still 0. This bond order tells us that this is not going to happen. Yes?
So it would always be 2 in the bonding, and whatever's left over is in the antibonding?
No, sometimes there'll be 8 or 19 or...
Okay. So how do you know how many would go in each?
Well, you draw the molecular orbital diagram, and you look at the number of valence electrons, and then you put them in.
Is it possible to get a negative number, and if so, what does that mean?
You can get a negative bond order, yes. A negative bond order just means that bond is not going to form.
So it's the same thing as 0.
Yeah. 0 or negative, not going to form. You can also get a fractional bond order.
Then what?
Well, if it's positive, it forms. If it's 0 or negative, well, it couldn't be 0. If it's negative, it doesn't form.
Can you get like 0.00001? Or just
I think that would be pretty hard, but we're going to see bond orders of 1/2. Those are pretty easy. So this is the He2 plus ion. 2 hydrogen atoms, but together missing 1 electron. And this has a bond order of 1/2. So here's a helium atom combining with a helium ion. Because when you combine those 2, then you'll get He2 plus. And I know that looks weird, and we haven't dealt with that, and it's very unusual, and this is the only place we're going to see it. But we can do it. And so again, you get the antibonding and the bonding orbitals. Now you have 3 electrons. The first 2 go in the bonding because it's lower in energy. The third one has to go in the antibonding orbital. Now the bond order is different, right? Because there's 2 in the bonding orbital, and there's 1 in the antibonding orbital, and divided by 2, and that gives us a bond order of 1/2. Bond order predicts that this ion exists. It does.
I think what's confusing me is just that there's 1s orbital on top of 1s orbital on bottom line. I thought there was only 2 electrons in the 1s, or 1 electron in the 1s orbital.
Well, the reason that we have these 2 here is because we're combining a 1s orbital from this helium atom, and we're combining a 1s orbital from this one. And so when you take those 2 things together, you're still going to get 2 orbitals.
How can you have both a cylindrical bond and then one that's completely separated, the antibonding between 2 molecules?
Well, one of them is pulling the atoms together, and the other is pushing them apart.
Okay.
And so the bond order tells us that the one that's pulling them together is winning if the bond order is greater than 0.
Oh, and then if you have it...
If
at
the bond
0,
order is 0, it means it's a tie, so nothing's going to happen.
there's no reaction.
If the bond order is negative, then the antibonding, the pushing away, is beating out the pulling together.
I understand that it's an ion, but if it's the plus sign, doesn't it mean that one gets taken away? So I'm confused why there's still one in.
Well, helium normally has 2 electrons, and it only has 1 here.
Okay, and then can we do an example of something that we would have to make that with, and then if we didn't know, can we draw the?
Oh, we're not even close to done yet. So here's a summary of what we talked about so far. Molecular orbitals are approximated as linear combinations of atomic orbitals. The number of molecular orbitals formed equals the number of atomic orbitals you start with. So what we've seen so far is a 1s orbital from each atom. We're starting with 2 orbitals. We get 2 molecular orbitals. When 2 atomic orbitals combine, one is an antibonding molecular orbital and the other is a bonding molecular orbital. When you're putting electrons in the molecular orbitals, you fill the lowest ones first with up to 2 spin-paired electrons. And we do Hund's rule the same as we did when we were learning about electron configurations. If you have multiple molecular orbitals with the same energy, you put the electrons in singly first. In the quantum hotel, that was people taking their own beds before they had to share. In order for a stable bond to be present, you have to have a positive bond order, greater than 0. So let's do a simple example, and then we'll go on to things with p orbitals. So use molecular orbital theory to predict the bond order in H2+. Well, we need to draw the individual atomic orbitals for the 2 atoms involved here. So we've got, let's see how to do this best on my iPad. So we've got a hydrogen atom, and H2+, that means we're going to have a hydrogen atom and a hydrogen ion. So over here we've got H, and here we have the H+, and they each have a 1s valence orbital. The hydrogen atom has 1 electron. How many electrons does the hydrogen ion have? 0. So when these 2 combine, we get a bonding orbital that's called sigma 1s, and we get an antibonding molecular orbital that's called sigma star 1s. And we usually draw these dashed lines just to help us see where these came from. So this is our H2+. Molecular orbitals in the middle and the atomic orbitals on the side. So these are atomic orbitals, molecular orbitals, atomic orbitals, and energy going up. So how many total electrons are in this H2+? This 1. Where does it go? It goes in the bonding orbital. It goes in the bottom one. There are no other electrons. So this is asking us for the bond order. Bond order is the number of electrons in bonding orbitals. How many? 1. Minus the number of electrons in antibonding orbitals, which is 0, divided by 2. So the bond order is 1/2. We looked at the H2, and its bond order was 1. The bond order for this H2 bond was 1. This bond order is 1/2. Is this stronger or weaker? Weaker. It's weaker. The larger positive the bond order is, the stronger the bond is. 1/2 is just barely above 0, and so a bond will form, but it's going to be weaker.
Why is it weaker?
Because you have fewer electrons in bonding orbitals. Here there's only 1 electron in the bonding orbital, whereas in H2 molecule there's 2 electrons in the bonding orbital. So if you think of electrons in the bonding orbital as pulling together and electrons in the antibonding orbital as pushing apart. Here I've got one person pulling together. In the H2 molecule, I've got two people pulling together, and it's going to be a stronger bond.
Is the closer you get to zero, the more energy? by chance?
It'll be higher in energy,
Higher in
yes.
energy? Okay.
So a bond order of 0 means that the energy of the bond is the same as the energy of the individual atoms. And so there's no motivation for anything to happen.
But negative would be high energy because they want to.
A negative bond order means that the energy of the bond is actually higher than of the individual atoms, and so that's absolutely not going to happen. So, homonuclear diatomic molecules. Question in the back.
The bond order of H2 is 0, isn't it?
The bond order of H2 is 1.
Well, they both have 2 electrons.
So this is the H2 molecule. There's 2 electrons in the bonding orbital, and there's none in the antibonding. So 2 minus 0 is 2, divided by 2 is 1. So this is a bond order of 1. This one had a bond order of 0, and that doesn't form. Okay?
So if you, like, for the question that we just went over, if we didn't know H2, we could just draw it out and figure it out.
Yeah, you'd have to figure it out. Mhm. So we're looking at homonuclear diatomic molecules, again with the prefixes. So homo is a prefix that means the same. Nuclear, nucleus. Same nucleus, 2 atom molecules. So here we're going to look at the Li2 molecule. It's 2 lithium atoms. We will look at heteronuclear later, where you have 2 atoms that are of different elements. But we're not going to look at anything beyond diatomic molecules. So if we look at period 2, we did period 1, it's hydrogen and helium. Lithium is in period 2. Its valence electrons are in the 2s orbital. And so if we combine a lithium atom and a lithium atom and look at a bond that might form between those, combining 2s orbitals looks the same as combining 1s. You get a sigma 2s bonding orbital and a sigma star 2s antibonding orbital. Each lithium atom has 1 valence electron, and so when we put those valence electrons into the molecular orbitals, they occupy the bonding orbital. And this is going to have a bond order of 1. Any questions? Next is beryllium. So beryllium has 2 valence electrons, 2 electrons in the 2s. We combine the 2s orbitals, we get the antibonding and the bonding, but now we have 4 electrons to put in here. And so there's 2 in the bonding orbital and 2 in the antibonding orbital, and that gives this a bond order of 0, which predicts that Be2 is unstable, doesn't form. And that is consistent with experimental findings. Okay, after that, we get to p orbitals. So for boron, we have 1 electron in the p orbital, so we have to look at combining p orbitals. And I think this is actually easier to look at than the s orbitals. So p orbitals, remember, both of these lobes are part of 1 orbital. And one side is positive phase and the other side is negative phase. So if we take these 2 orbitals and combine them in a way that they're, I'm just going to call them blue and red because I can't remember which your book says is positive and which is negative. We've got blue and red corresponding to positive and negative. If we overlap these or linearly combine these so that the blue parts overlap, then we get this big bulgy blue part. Does that make sense? Because blue and blue makes it bigger. If we combine them, if we flip this one over so that we're combining blue with red, then these cancel each other out. This lobe out here isn't really affected, but this part in the middle, we cancel that out. Yes?
I think that would be opposite, give you charges, attractions.
But this isn't charges, this is phases of a wave.
Okay.
okay?
I thought you said corresponds to positive and negative.
A
so it's-
positive phase,
Gotcha.
positive phase and negative phase.
Like bubble waves, and when they match up, they get bigger. And
Sort of,
They cancel
yeah.
out. It's like the opposite
You know,
effects.
we looked at the string video, right?
Mhm.
And we see how one part of the wave goes above the horizontal line and one goes below. The
That-
part going above is positive, the part going below is negative.
So that's like two positive sides then.
Yeah, this would be like putting two positives together or two negatives together. It's going to make it bigger. And this is putting opposites together and they cancel each other out. This also makes a sigma molecular orbital. Because if you stuck your eye right here and looked down through both of the nuclei, you'd see a cylinder, right? It's symmetrical. So this is a cylinder, so we get sigma 2p and sigma star 2p. So we have the bonding and the antibonding. Again, the antibonding is higher in energy and the bonding is lower in energy. But there are 3 p orbitals. So in the, for the 2p x orbitals, those are aligned along the x-axis. They will run into each other end to end, right? The y orbitals, you know, this is an attempt at perspective drawing, so those are sticking in and out of the plane of the screen. So in and out, and these can overlap, but they're going to overlap side to side. And here, when we overlap them constructively, the red parts add together and the blue parts add together. And so we get these funky shapes like this. When we flip one of these and add them together, then we get this big node in the middle, we get an antibonding orbital. These are called pi molecular orbitals. Just like we had with the pi bonds in valence bond theory, it's a side-to-side overlap.
What kind of experimental data are these orbitals based on? Because I thought the atoms are so really, really tiny, you can't really tell what shape they are.
Well, they are tiny. We can't see these things, but they've developed the equations for all these wave functions, and
So
they
it's
can
mostly based on
approximate.
math.
It's basically based on math and how well this predicts what we actually observe. Yeah, we cannot actually observe these different orbitals. But we find that if we combine these wave functions in this way, that it does describe accurately a whole bunch of other observations. So these are pi 2p, pi star. So antibonding is the star. And then there's a third set of p orbitals, right, in the z-axis. And they're also going to do that side-to-side overlap and form a bonding orbital and an antibonding orbital.
Why didn't they just do the y up and down like that, and the z, the weird one?
I don't know.
Okay.
You could change the z's for the y's if you like. Yeah. The relative energy ordering for these molecular orbitals that we get by overlapping the 2p atomic orbitals, unfortunately, is not the same for all of the molecules. We've got the sigma star, and we've got 2 pi's and 2 pi stars. And how those order are a little different. They determine it using math. So we're just going to have a little rule of thumb. And the typical ordering is this one, where the sigma 2p is lower than the pi 2p, and the next is pi star and sigma star. This is what's considered typical. And for things like oxygen, fluorine, and neon, that's what we observe. We do not observe this for boron, carbon, and nitrogen. So this is the expected order. So we've seen this part at the bottom before. Here we've got the 2s and the 2s, and they make a sigma and a sigma star. This is how the p orbitals overlap. We get a sigma and a sigma star from the end-to-end overlap of the pi orbital, the p orbitals that are pointing to each other, And then we get the side-to-side overlap from the other two p orbitals. So the bonding is always lower in energy than the antibonding. And sigma is lower in energy than pi for the most part. This is what we expect. For boron, carbon, and nitrogen, what happens is these two are flipped.
Are those supposed to be octahedrals, or they just look like that?
They're not supposed to be octahedrals. So the way you remember this is be careful now. Boron, carbon, nitrogen. Boron, carbon, nitrogen, be careful now. Those are the three where it's flipped. And it's just these two right here. This is very nice and symmetrical, right? The sigmas are on the outside, the pi's are on the inside. In this one, pi star and sigma star stay the same, but these two switch order. Okay?
I was gonna say about why.
Why? This is why. There is more mixing of the 2s and the 2px for boron, carbon, and nitrogen, and that causes these two to be switched in energy. So it has to do with how much the s and the p orbitals mix together.
So are there gonna be problems like that, and it's gonna make us figure out the
Yes.
figure all this?
Well, yeah, let's keep going here. So these orbitals, these molecular orbitals are more spread out in energy than these are. We don't need to remember that. We just need to remember that these are switched in order. Okay, but that's just the explanation for those of you who want to know why. Some of you are content with just, okay, I'll memorize that and we'll call it good. So this is looking at the rest of period 2. So here's boron, carbon, nitrogen, oxygen, fluorine, and neon. So this is the be careful now group where the pi bonding orbital is lower in energy than the sigma bonding orbital. So for boron, each boron has 3 valence electrons. And so we're going to put 6 electrons in here, 2, 4, 5, 6. And we can look at the bond order. There are 2 and 2, 4 electrons in the bonding orbitals and 2 electrons in the antibonding orbitals. 4 minus 2 is 2 divided by 2 is a bond order of 1. C2. Well, now we've got 2 more electrons. So those 2 electrons are going to go into this pi, these 2 pi bonding orbitals, and fill those up. Now the bond order goes up to 2. And then we've got nitrogen, another 2 electrons. And so those go into the sigma bonding orbital. Nitrogen has a bond order of 3. We can see that as the bond order increases, the bond energy increases. That means that the bond is stronger. And we see that the bond length decreases. That also indicates strength. Because the bond is stronger, the atoms are held closer together. Yes?
What exactly is the difference here between the sigma and the pi? Is pi always for p, or?
Only p, s orbitals cannot make pi molecular orbitals because they cannot do a side-to-side overlap. Pi and sigma in molecular orbital theory are similar to the pi and sigma bonds in valence bond theory. A pi bond in valence bond theory happens from a side-to-side overlap of 2 orbitals, 2 p orbitals. And these pi molecular orbitals happen by the side-to-side combination of 2 p orbitals. You start with 3 p atomic orbitals. From each atom, you need to end up with 6 atomic orbitals. And the way they combine is this 1, 2, 3, 4, 5, 6. When we get over to oxygen, fluorine, and nitrogen now, the order of sigma 2p and pi 2p is reversed. This is the normal ordering. This is the weird be careful now ordering. Oxygen, each oxygen has 6 valence electrons. Yeah, brain farting. 6, so we've got 12. So then in our molecular orbitals, we've got 2, 4, 6, 8, 10, 11, 12. Bond order is 2.
For nitrogen, you took the sigma 2s and sigma 2p and the pi 2p and added those two and subtracted by the sigma 2 star, right? That's
Right.
what you got for the bond order.
Yep, so we've got these guys are bonding, and this one's bonding. That's a total of 2, 4, 6, 8. And then this is the anti-bonding, minus 2. So that gives us 6, but it's divided by 2. So that gives us our bond order of 3. So that's oxygen, fluorine, 14 electrons, 2, 4, 6, 8, 10, 12, 14. Bond order goes down to 1. Neon, total of 16 valence electrons, 8 from each. And that fills all of these up. Now the bond order is 0. What does a bond order of 0 tell us?
Doesn't occur.
Doesn't happen. There is no diatomic neon molecule.
Can you say that for pretty much any of the noble gases?
That's correct. None of the noble gases will form diatomic molecules.
Can you write that on the side for me with the numbers to do the bond theory?
The bond order for neon?
Yeah.
Sure. So bond order for neon, we've got, let's see. These are, I lost my pen. That's bonding. This is bonding. These are bonding. So we've got 2, 4, 6, 8 electrons in bonding orbitals. And we've got 2, 4, 6, 8 in antibonding orbitals, divided by 2, and that's 0. Okay?
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid. When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic. Paramagnetic substances have unpaired electron.
Yeah, it's cool. It's also very short.
Onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic.
Okay, see this? Probably. It's a YouTube video I found. So the liquid nitrogen, you pour it over, this is a really strong magnet, you pour it over the magnet, and just like you would expect, it just goes straight through, right? But the liquid oxygen gets stuck. The liquid oxygen interacts with the magnetic field. That's why it's sticking there. Any questions? Let's see if I can get back to my slides now. So that experiment shows us that oxygen is paramagnetic, right? It interacted with the magnetic field. Paramagnetism, as we discussed earlier, is a result of unpaired electrons. Lewis theory and valence bond theory do not explain this. Here's our Lewis structure for oxygen. Do you see any unpaired electrons? Nope. Here's the valence bond theory model for oxygen. We have this sigma end-to-end overlap of the p orbitals in each oxygen, and we have the side-to-side overlap of p orbitals in each oxygen, and then we have lone pairs. Are there any unpaired electrons? No. And yet we just saw the oxygen stick in the magnetic field. here's the molecular orbital diagram for oxygen. What does it have? 2 unpaired electrons. Molecular orbital theory explains something that the other 2 theories do not explain. Yes?
So is that also true that it's stuck more than nitrogen because it, like the energy's higher? So the bond.
It has nothing to do with the energy being higher. It has to do with there being unpaired electrons. So aluminum, good luck sticking magnets to aluminum, right? It does not respond to magnetic fields. But iron does. So oxygen sticks in that magnet because it has 2 unpaired electrons. The nitrogen didn't. Look at nitrogen. No unpaired electrons. This is also evidence of, no, never mind. No, it isn't. Because I realize it isn't true. You can't make me say it. So let's draw a molecular an MO, energy diagram, and look at the bond order for the N2 plus ion. And then they're asking us, do we expect that to be stronger or weaker than the nitrogen molecule? And is that ion diamagnetic or paramagnetic? Yes?
So that's how magnets work, do they have an unpaired electron?
I am rusty on exactly how magnets work. I know in order for a substance to interact, be attracted or repelled by a magnetic field, there have to be unpaired electrons. Off the top of my head, I don't remember why something is a magnet in the first place. I could look it up, but I can't do that right now. Yeah, it's a good question though, and we should look it up. Okay.
Sorry, I know, I'm just dragging it on.
We will look it up. I promise. We'll look it up, but not right now. We're going to do this right now. So to draw the molecular orbital energy diagram, first we're going to start by looking at the atomic orbitals for each atom involved. So we're looking at N2 plus. That means we've got an N over here, and we'll put an N plus over there. You could put the plus on the left side. It doesn't matter. But one of them must be short an electron. We're looking at valence electrons only. So we've got 2s, and we've got 2p. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. And then over here, same orbitals, 2p and 2s. Because this is an N plus, it only has 4, 1, 2, 3, 3, 4. Then we have to combine those. So for the s's, we're going to get a sigma 2s and a sigma star 2s. And this is where drawing on the chalkboard is actually easier. Combining the p orbitals, we're going to get 2 pi bonding and antibonding each, and 1 sigma bonding and antibonding each. And the question is what the order is. I'm going to start at the top. I'm actually going to erase some of this because I don't have enough space. So I'm going to make a little room in here. So we're going to have a sigma 2p star at the top, and then a pi 2p star. The other two were the ones we had to think about. Nitrogen is one of the be careful now, right? So it's reversed. The nice symmetrical order, can't point like that, would be sigma star on top and sigma at the bottom and both of the pi's in the middle. Be careful now says those are switched. So the sigma is here and the pi bonding is there. And these all come from here. I know it's a mess, right? So, you know, I give exams that are mostly multiple choice, right? And then there's some problem things. So I'll just tell you right now, there will be at least one question where you have to do something like this on the exam. And there could very well be a problem like this on the final exam. As a multiple choice question, the way this ends up being is I'd give you multiple molecular orbital diagrams all filled out, and you have to pick the correct one. That's easier than drawing it yourself, right? And just for my own sanity in grading, if I gave this to you as a you work it out type problem, I'd probably give you the template, or maybe I'd give you two templates, the regular and the reversed order. You'd have to choose which one to use. You'd have to figure out how many electrons and stick them in appropriately, okay? But I'm not going to make you draw this because I don't want to look at it. I don't even like looking at my own drawing of it. It's ugly, right? Okay, back to what we were doing here. So we got our molecular orbitals drawn in. Now we look at the total number of electrons. We've got 5 over here and 4 over here. That's 9. And so we're going to put those into these orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? Got them put in that way, and then it's asking what the bond order is. Well, which of these are bonding orbitals? Got this one, that's a bonding orbital. This is a bonding orbital, and that's a bonding orbital. How many electrons in those bonding orbitals? 7. So bond order equals 7 minus 2 antibonding electrons over 2.
So you always start filling from the bottom to the top?
Yes, you always fill from lowest energy to highest energy. So 5 halves or 2.5. That's our bond order. Do you remember what the bond order for N2 was? 3. So is this bond stronger or weaker than N2? Weaker.
And just make sure the open one, on this one, what's split is sigma star and pi star, right?
Yep, this one and this one. Those are the two that can flip.
Okay.
Now the other question is here, is this diamagnetic or paramagnetic? It's paramagnetic. So this would, because of this one unpaired electron here, this would interact with a magnetic field, whereas N2 does not. Questions? Make sure you didn't miss anything. It's paramagnetic because it has an unpaired electron. So these are, we're going to look at a couple of heteronuclear diatomic molecules. So here, the two atoms are not of the same element. So here's the Mo for no, right? The molecular orbital diagram for nitrogen monoxide. Oxygen is more electronegative, and so its atomic orbitals are a little lower in energy than the nitrogen atomic orbitals. And that's not really something I expect you to remember. When these combine, though, they're not coming equally, right? And so the lower atomic orbital, the lower energy atomic orbital has more effect on the bonding orbital, molecular orbital, and the higher energy atomic orbital has more effect on the antibonding. And here we've got the splitting here with the sigma star, pi, and sigma. Now, a good question is, okay, we've got nitrogen that does the reversing of the order and the oxygen that doesn't. How do we know which one? I wouldn't give you a question like this because you wouldn't know from what So we're just telling you this is what the order is. So it's going to use the regular order. And then all of the electrons from the oxygen and from the nitrogen are put into these molecular orbitals. Is this a stable molecule? Well, how do you decide if it's a stable molecule? Bond order. So bond order, count the bonding electrons. There's 2, 4, 6, 8. So we've got 8 electrons in bonding molecular orbitals, and we've got 1, 3. Total of 3 in antibonding, divided by 2. So that's 6 divided by 2, that's 3. So this is a stable molecule. Yeah. Well, I was just hoping that today we could change the rules of math and make 8 minus 3 be 6. You don't think I can get the rest of the universe to go along with that? Fine.
I'll go with this.
You'll go with it? Thank you. And join me. This will be 8 minus 3 equals 6 to 8. Okay, 2.5. Is it stable? Yes.
Pretty stable.
So will we, so I know that you were saying like we wouldn't know this, so would we not make an orbital thing like this?
If I gave you a question about something like this where you have one that reverses the order and one that uses the normal order, I would not trick you. I would not have the difference between them be that one had reverse order and one didn't. But the kinds of questions you should definitely be able to answer about something like this is, what's the bond order? Is it paramagnetic or diamagnetic? So which is it, paramagnetic or diamagnetic? Paramagnetic. It's got an unpaired electron. Okay?
Now, how do we make that with two different molecules?
You mean, how do you make nitrogen monoxide?
Like, how would you make that diagram thing if you,
Oh.
if you had just said make a diagram?
I would expect your diagram to look exactly the same as if they were this. I wouldn't expect you to do relative ordering of these are a little lower, these are higher. I wouldn't expect you to know that.
But how do we, I guess what I'm asking is how do we make the two different diagrams in the same picture? Like, because there's the blue on the bottom and there's like the peach colored boxes on the top, so how do you make two?
Well, this is just like what I drew in the last example,
Okay, so,
right? They just use blue to indicate the S and peach to indicate the, but it's the same. This is the nitrogen with its 2s and its 2p atomic orbitals, and this is oxygen with its 2s and its 2p. And then these combine, it's all the same, they just colored it. Interesting thing with hydrogen and fluorine. Hydrogen's so electronegative that its 2p orbitals are actually lower in energy than hydrogen's 1s orbital. And so when these guys bond, the s orbital interacts with one of the p orbitals to make this sigma bonding and the sigma star antibonding. But the hydrogen doesn't have any other orbitals really to interact with these p orbitals. And so the other two p orbitals are just left as non-bonding. Okay, so let's use molecular orbital theory to determine the bond order of the FO minus ion. Is the ion paramagnetic or diamagnetic? So here's an interesting question. If you have an odd number of valence electrons, could it possibly be diamagnetic with everything paired up?
Everything's paired.
You can't have all paired electrons if there's an odd number of electrons. So if you have an odd number of electrons, it has to be paramagnetic. This one, though, is an even number. So I'm going to put fluorine on the left.
What about a triple bond with a lone pair?
It's still pairs, right?
Yeah.
So here's fluorine. We got 2p and we got 2s. How many valence electrons does fluorine have? 7. 1, 2, 3, 4, 5, 6, 7. And over here is going to be oxygen. I got to give the minus to somebody. I'm going to give it to the oxygen for no particular reason, and it's not going to affect the our ultimate answer. 2p and 2s. Oxygen itself, as an atom, has 6 valence electrons. Now with an extra one, we've got 7. We've got 1, 2, 3, 4, 5, 6, 7. And then we have to draw all the splitty things. So we had sigma star 2s and sigma 2s. And then we've got sigma 2p and pi 2p and pi star 2p and sigma star 2p. How many electrons am I putting into the molecular orbitals? 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Bond order. Looking at the ones without the asterisks, so this is bonding, there's 2, 4, 6, 8. 8 electrons in bonding orbitals. In antibonding, 2, 4, 6. So 8 minus 6 over 2, pretty sure that's 1. The bond order is 1. Do we predict that this is a stable molecule?
Yes.
Yeah. Is it paramagnetic or diamagnetic? Diamagnetic. Any questions?
Why is the 2p within the diagram just the 2 boxes and not 3?
Because 2 of the boxes made the sigma 2p's.
Okay.
Because that was the end-to-end overlap, and then the others are side to side, up and down and sticking out. Okay, so now we get to what I like, the fun part. Why the heck did we do this at all? Okay, so remember we looked at ozone when we talked about resonance structures in Lewis theory? And we could draw 2 Lewis structures, but experimentally we know that the bonds here are the same length and strength. And so we don't have a single and a double and a single, and we definitely don't have things vibrating back and forth. It was actually more like a 1.5 bond, but we couldn't really show that in Lewis theory, and so this was the best we could do. Valence bond model also predicts a double bond between 2 of the oxygens and a single bond between the other oxygen. Again, doesn't match up with experimental observations. In molecular orbital theory, the pi molecular orbitals form from p orbitals on all 3 atoms, and they are delocalized over the entire molecule. So you can have that half bond spread out. So you can essentially have a 1.5 bond here and a 1.5 bond there, instead of having to choose a double here and a single there, or vice versa. That second bond is spread out over the entire molecule. This explains what we observe experimentally, that the bonds are of equal length and of equal strength. Any questions? Because molecular orbital combines the atomic orbitals into orbitals that can be shared over the entire molecule. Yes?
Can it just not form a triangle?
It cannot form a triangle. It will not.
Like everything else.
Part of that is bond angles. Okay? So the bond angle here from Lewis theory is predicted to be what? You got 3 groups here?
180.
No, 3 groups.
Trigonal.
120, right?
Oh, the actual.
Right? What would the bond angle be if we made a triangle out of it?
So 60.
60. That's a lot smaller angle. There's going to be a lot of strain if we try to do something like this, where we've got oxygens making a triangle.
Gotcha.
You could draw a Lewis structure like that, but it's not going to work. But this is what's actually going on. All of those things that have resonance, this is really what's going on. We've got delocalized molecular orbitals that are spreading those electrons out over the bonds that have the resonance. Benzene is a really important molecule in organic chemistry and lots of benzene derivatives. Lewis model draws this as alternating double and single bonds around this 6-membered carbon ring. It is very cool. But what we know is that these bonds are actually all equivalent, and this is the molecular orbital representation, that those form a delocalized orbital over the entire molecule, and that explains why we have 6 identical carbon-carbon bonds in that ring. That took way longer than it did yesterday.